Okay, so my title, Large Area Surveys for Black Carbon and Other Light Absorbing Impurities in Snow. And I'll start out with the Arctic, and I'll also show Antarctic, North America, China, and now we have some results from Chile. So we'll finish with Chile. So starting with the Arctic, my co-workers were Sarah Doherty, Dean Haig, Tom Brentfeld, Rich Brandt, and Tony Clark. And we are addressing this question, soot. We call it soot, I guess the Spanish is from from industrial sources and from forest fires, darkens the snow, makes it melt sooner. Would a reduction of soot pollution help the Arctic snow to last longer? So that's our question, and we use the quantity albedo, which is the fraction of light reflected by the snow. So the ratio of the reflected sunlight to incident sunlight, number between 0 and 1, or 0% to 100%. Snow has the highest albedo of any natural surface. Oh, I'm sorry, I need to turn this on. And its albedo is variable. Well, first of all, it varies with wavelength, but then integrated over wavelength. It varies with the snow grain size, that's the most important thing, which it normally increases as the snow ages. The small grains are, the large grains grow at the expense of small grains. Snow depth, sun angle, and impurities. Those are the other important variables. Why is snow grain size important? The way light re-emerges from snow, comes in, and it goes back out. Most of it goes back out. And the photon has a chance to change direction when it comes to a boundary between air and ice. And so the way that light re-emerges from snow is by successive refraction. And while it's traveling through the ice, it has a chance to be absorbed. So comparing fine-grained snow to coarse-grained snow, to get the same number of refraction events, the distance traveled through ice is greater in the coarse-grained snow. Therefore, coarse-grained snow has lower albedo. It's more absorbed. This is a millimeter scale. Here's some snow grains showing, the typical sizes for grain radius would be 50 microns to 1,000 microns. Millimeters, 1,000 microns. And then these were our calculations from 1980. We were making a radiator transfer modeling of snow albedo. So this is the albedo from 0 to 1. There's a bunch of wavelength in the ultraviolet, visible, and then near infrared. Albedo is very high in the visible and the ultraviolet, so that's why it looks so bright. That's what we see. And most of the absorption is in the near infrared. And in the near infrared, it's very sensitive to grain size. These are calculations for different grain size, grain radius of modeled snow. This would be typical of new snow, 50 to 100 microns, and then old melting snow, about 1,000 microns. And in the visible, the albedo still stays high, but in the near infrared, it becomes sensitive to grain size. Impurities are what we're mostly going to talk about today. Why are impurities so effective in reducing snow albedo? They affect the albedo in the regions where the albedo is high, the visible and ultraviolet. Absorption by ice is very weak at visible and ultraviolet wavelengths. Ice is nearly transparent, so very small amounts of absorptive impurities can reduce the albedo. Most important ones are soot, or black carbon, and soil dust. So here's our calculations back from 1980. So this is the plot of albedo again versus wavelength, and this was for pure snow, the top line. Then if we add different amounts of soot, up to 5 parts per million, you see it reduces the albedo in the visible and ultraviolet region, but not in the near infrared, where absorption by ice is strong, so that small amounts of absorptive impurities cannot compete. These two plots, one is for fine-grained snow, 1,000 microns, and the other is coarse-grained snow. You see this 5 parts per million plot, the albedo is reduced by adding soot, but it's reduced more in the coarse-grained snow. the same amount of soot has a bigger effect on coarse-grained snow than on fine-grained snow because the light penetrates deeper in the coarse-grained snow and encounters more soot. What is in the snow? Well, this was first investigated for the Arctic by Tony Clark and Kevin Noon when they were both at University of Washington. They were students of Bob Charleston, as was Tammy Bond and Sarah Doherty. Yes. So yeah, and then Tony continued to work with us on this. He was inspired by a talk I gave when I was interviewed for the job at University of Washington. They were able to contact researchers who were going to be in the Arctic and ship samples back to them frozen to Seattle. So they got samples in 1983 and 1984. And at these blue locations, Alaska, Canada, Greenland, Svalbard, Scandinavia. They got 60 samples, and most of the amounts they found were 5 to 50 parts per billion, parts per 10 to the 9th, or nanograms per gram. So they said 5 to 10 parts per billion of black carbon could reduce the albedo by 0 to 4%, depending on the snow grain size. You can sit up here. There are some chairs that are unused right now. Their average in their 60 samples is 25 parts per billion, which implies an albedo reduction of about 2% for the Arctic. So that would be significant for the climate of the Arctic. However, let's compare it to how you can reduce snow albedo by putting black carbon in snow, or you can reduce that snow albedo by increasing the grain size. Grain growth, snow aging from new snow to old melted snow, grain radius 100 microns increasing to 1,000. Albedo, broadband albedo, average over the solar spectrum, 83% down to 71. So you get a reduction of albedo by 12%. If you got black carbon of 20 parts per billion, you get somewhere around 1% reduction of albedo. So that means for albedo, snow grain size is more important than soot content, but grain size is probably more difficult to predict. Also important is snow depth. Thin snow, of course, the light penetrates through to the underlying surface, and in the Arctic snow is thin. It's thin and patchy, so you get the maximum albedo if you spread out the snow uniformly. If you have it in clumps, then you've got a lower albedo, which means surface albedo calculation in a climate model should use a frequency distribution of snow depth, and that's now just starting to happen. Albedo computed from the average snow depth will be too high. Another important thing to note is that soot in snow is hard to detect visually. You look at these pictures, I can't tell from looking at these pictures that one is grossly polluted by soot and the other is not. The one on the left is downwind of the dirty industrial city of Vorkuta, 370 parts per billion. And this is the Greenland ice sheet, the cleanest part of the Arctic, only 2 parts per billion. So the particles are tiny, submicron, they're just gray. Visually, you can't really tell. If you do visually see impurities in the snow, more likely they are silt and sand, in this case, this is actually ice, not snow, on the edge of the Greenland ice sheet. Where and when does the variation of snow albedo matter for climate? It matters whenever large areas of snow are exposed to significant solar energy. So that means snow albedo is less important in the winter when there's not much sunlight, and less important in the forest where it's hidden by trees. So for the Arctic snow, the tundra in the spring, covering the sea ice in the spring, the Greenland ice sheet, there's snow both spring and summer. Non-Arctic snow, the Great Plains of North America, the steppes of Asia. Sea ice is, even when it's not perfect snow, it still has a high albedo, so it's matters as well. The Arctic glaciers in the summer. Then finally, mountain glaciers are too small to be important for climate, but they're important for hydrology. So there is some studies, including what we've done here in Chile, of black carbon and other absorbers in mountain glaciers. Actually, we did not get to the glaciers on this trip, but we got close. So here's my outline. First, we're using a photometric method to measure black carbon and other light-absorbing impurities. How do we verify the radiative transfer modeling of the albedo reduction? Then our survey of Arctic snow, how we separate black carbon, composition by black carbon from other absorbers, mineral dust and brown carbon, source attribution of black carbon, vertical redistribution, what happens to the black carbon when the snow melts, and then how much black carbon has changed over the last 25 years since Clark and Newman. Then we go to Chile, North America, or sorry, China first, then North America, then Chile. Well, I need to explain our strategy to estimate albedo reduction in natural snow. For the Arctic, why did we collect 2,000 snow samples but made only a few albedo measurements? The reason is that the climatic effect of black carbon on snow, albedo, is expected to be at most a few percent, which is comparable to the accuracy of the albedo measurements. And snow albedo depends on several other variables, particularly snow grain size. You make a measurement of albedo, you don't know why it has that albedo. Therefore, we do not directly measure the albedo reduction. Instead, 2 steps. We collect snow samples, we melt and filter them, we analyze the filters in the spectrophotometer for the black carbon concentration. Then we use that black carbon amount together with snow grain size in a radiative transfer model to compute the albedo reduction and compute it for a variety of grain sizes. Because we do it this way, well, first let me just say there are other ways to measure black carbon. Thermal optical, SQ2. The advantages of our filter method, one is that it is a measure of absorption. We actually measure the absorption by filter, so it's directly related or closely related to the absorption in the snow rather than a mass of black carbon. It's the absorbing by black carbon. The filtering can be done anywhere. No need to bring large quantities of snow back to Seattle. If we have a lab, we will use it. If not, we can set up in a hotel room. Or in one case, I actually put a clean lab inside a big tent in northeast Greenland and did my filtering in the tent. So we'll get filters that look like this, and we can actually make some assessment while we're still in the field because we brought along a set of standard filters with known amounts of black carbon. We can visually compare them with what we're getting. And that visual estimate compared to what the spectrophotometer gives, it's within a factor of 2 generally. So we can get some idea before we go back home. Now what we actually get is an absorption coefficient of square meters absorption cross-section area per gram of snow. That is a quantity that's not so easily communicated among disciplines, so we convert it. What we get there is absorption cross-section of particles on the filter divided by the amount of meltwater passed through the filter. We convert it into a mixing ratio, grams of black carbon per gram of snow by means of the mass absorption cross-section, square meters per gram of black carbon. And our black carbon amounts are calibrated relative to filters with a commercial soot that has a mass absorption cross-section of 6 square meters per gram at 550 nanometers wavelength. Now we need to test or verify or not verify the modeling of albedo reduction or bypass the model. Here's how we do that. Or we say that direct measurement, actually we thought we might be able to do direct measurement and attribute albedo reduction, but we conclude that's unlikely to be feasible in nature because of complicating factors. The vertical variation of snow grain size, vertical variation of soot content, and because the natural soot content is small, so the albedo reduction is kind of at the uncertainty level of the measurement. Also, you need deep snow, so there's no penetration to the ground below, and accurate shadowing. The instrument itself shadows the snow. Therefore, we think that artificial snowpacks are needed with uniform grain size and large uniform soot content, parts per million, not parts per billion. So you get a large signal on albedo, like 15% instead of 1%. That's being done with artificial snowpacks in the laboratory. There are a couple of groups doing that, and then the one that we're pursuing, or haven't pursued, is with Rich Brandt. We're doing it outdoors. Rich Brandt lives in upstate New York, which has cold winters, suitable for making snow with a little snowmaking machine. Advantages of an outdoor experiment: you have uniform illumination compared to a laboratory experiment. You have uniform illumination across the snowpack. You need a wide sample to avoid edge effects because light travels long distances in snow. It emerges from the snow horizontally distant from where it entered. You can make an albedo measurement. In the lab, instead you'd be making a bidirectional reflectance measurement. There are no standards needed. You just measure you look up, you look down. Disadvantage is the weather has to cooperate. And so far we actually only had one experiment that really succeeded. So he takes 4 hours to build a suitable snowpack and does that at night. And then he has over here a soot suspension and then a valve. So the soot suspension can be entrained into the water stream, and then you can make a dirty snowpack. So 1 part per million means you need to put 3 grams of soot into 3 tons of snow. And the water comes out sprayed as little droplets. They're almost spheres. And then in the morning, he measures the albedo of the 2 snowpacks, one dirty and one clean. So these were filters from the clean snowpack. This was from the dirty snowpack. Actually, that filter is too dark to measure, so put less water through it, and then you get something that's measurable. So we made the albedo measurements and collected samples of the snow and then filtered them the way we normally do with. And then he gets this plot of albedo versus wavelength, and this is the clean snow, this is the dirty snow, just as we would expect. It reduces the albedo in visible and ultraviolet, not in near infrared. And in order to explain those, we needed 2.2 parts per million, and what we got from the filter measurement was around the same thing. So to that level, we can say we verified the radiative transfer modeling. Okay, then on to our survey of Arctic snow. What we're trying to do, well, we've done it, to get better geographical coverage than Clark and Noon and to compare measurements made 25 years apart. So now we published that in 2010. So we got about 1,600 and probably now 2,000 snow samples that at all these locations. We collected a lot of them ourselves, but also we got a lot of volunteers collecting snow samples for us. We did Arctic Canada, some sites in Greenland, Svalbard, and Russia, whereas volunteers collected samples in the Arctic Ocean and also subarctic Canada. What we do, we like to go in the spring, get the snow at its maximum depth before it starts melting. That way we can sample at different depths and collect snow that fell at different times during the winter. So typically every 5 centimeters, for example. Then in Russia, we would have to fly into a city, and then we have to find a way to get out of the city to get the background natural snow. So that's why the dots of locations are fairly near those cities. To get out of the city, we would find some vehicle and we would drive out on a road or on a frozen river, or in this case on the Arctic Ocean. And then we have to get away from the road. So we would walk, and in some cases we would actually collect samples 300, 600, 1,200 meters away to see that we've gotten far enough away from the road. Here we are on one of the world's great rivers, the Lena River, near its delta. And then, again, filtering in a hotel room. In Canada, we've got Arctic Canada. We got samples at 24 locations, and on lakes, sea ice, tundra, and ice caps. And comparing those 2 projects, in eastern Siberia, we got 350 snow samples in 2 months. Arctic Canada, we got 300 samples in just 2 weeks. Why was it so much more efficient in Canada? That's because we had the use of a ski plane that could just land anywhere in a remote place, and we just walk away from the plane a short distance and collect our snow. This plane well, it's got convertible landing gear. It can land on skis, or, it can land on wheels, but then it can retract the wheel, and then a little ski goes down under where the wheel was, so it can land on skis as well. And then there was a cold storage location up in the front of the airplane. These are the average values versus vertical averages of our samples in parts per billion. You can see they're ranging kind of from 5 to 15. And then if you take the median of all these, you come up with 8. So here's our summary for the Arctic, Arctic Ocean, Arctic Canada, subarctic Canada, Greenland is the cleanest part of the Arctic, probably because it's at high elevation, the Greenland ice sheet, and the pollution stays mostly in the boundary layer. It does not get up to the level of 2,000 meters of the ice sheet. Russia was the dirtiest part of the Arctic, around 30 or so, 20 to 30 parts per billion. Svalbard, Scandinavia, sort of intermediate. So these are our median values from about 1,600 samples. Then we also had the opportunity, we try using our spectral measurements to separate the contributions to absorption by black carbon and other constituents. The way we do that is basically based on the color. Some of our filters look brown, and others look gray. The gray ones are black carbon, the brown ones are probably soil dust, or they could be brown carbon that's also in soil. So we will make a measurement from the spectrophotometer of the absorption optimal depth versus wavelength. Actually, we don't go down this far. Some of this is extrapolation, but this lower one is what black carbon would do. And this is one of our field samples that's more brown. And so it has a steeper wavelength dependence. And by that wavelength dependence, we apportion the absorption and then multiply it through by the solar spectrum, and then get a fraction of the total solar energy of the solar energy that is absorbed by particles, not by ice, how much is due to black carbon, how much to others. So now I've added a column to this table. I already showed you this column, but now the estimated fraction of absorption due to non-black carbon is through the Arctic, it's around 40%, except in the European part is somewhat lower. So that was a little bit of a surprise to us that it's not just black carbon, it's also other things. And then, but of the black carbon, where does it come from? Does it come from industrial sources or forest fires and other biomass burning? Well, that was done by Dean Haig, who was in my department. We collected, we saved samples of meltwater, which he then analyzed for 22 chemical species to get kind of a fingerprint. Got 4 empirical orthogonal functions, and concluded that industrial sources dominate in the North Pole region and in Svalbard, but biomass burning dominates elsewhere in the Arctic. He also separated grass fires from forest fires. Canada was grass fires, Russia was forest fires. So that was a little bit of a surprise to us. We thought it was going to be mostly industrial sources. Another question is what happens when the snow melts? Black carbon is hydrophobic, so we hypothesized that when it's stuck to a snow grain, when its snow grain melts, it won't dissolve in water, it won't wash away with water, it'll just go stick to another snow grain. So that was our hypothesis, that you've got snow, it's got black carbon in it, as the snow melts, it leaves the black carbon at the surface, where it can have a much bigger effect on albedo than if it's uniformly distributed. So we tested that. One place we tested it is in southern Greenland, in the percolation zone. That's so this is a region in southern Greenland where it snows about 1 meter, and then during July, half of that melts. And that 1 meter of snow has about 2 nanograms per gram of black carbon. What happened to the black carbon in that half meter that melted? So we wanted to find out what's the vertical distribution. So we sampled this snow pit. We started out every centimeter, and then we went to every 2 centimeters, and we went down 2 meters. So we got through several annual layers, actually. That's Sarah Doherty on the left. That's me on the right. So here's our vertical profile from 0 to 200. And we see, look, it's about 2 parts per billion, but there's this enhanced summer melting. It definitely did get left behind at the surface. So in the summer when it's melting, we can have quite a bit higher, 20, 30, 40 parts per billion. Then we go down, and at 60 centimeters, we see last summer's layer buried now. And then there's another buried summer layer. Okay, which actually is related to a lot of discussion about what's happening in Greenland. A summer of intense melt on Greenland would result in a high concentration of black carbon at the surface. But in reverse, a high concentration of black carbon at the surface would cause enhanced melting in the summer. So there's a feedback. You have more black carbon, you have more melting, but if you have more melting, you have more black carbon at the surface. Okay, so we did that in Greenland, also in Alaska and in Norway, and published that last year, and we conclude that only 10 to 30% of the black carbon is removed with meltwater, and the rest remains in the surface. Okay, now we can compare the Arctic now to the Arctic 25 years, or now 30 years ago. We have some evidence from continuous measurements of black carbon in the air. This is at a station at the north end of Canada, 83 degrees north at Alert. The black carbon measured in the air, it goes through a seasonal cycle. So this is 1989 to 2008. If the air is dirty in the winter and is clean, winter and spring, and it's clean in the summer. So this is the so-called Arctic haze that it gets removed from the atmosphere in the summer. But the envelope of these values, the high values in the winter, you can see there's a decline with time. What do you think is the proposed explanation for that decline since 1989? Why has the Arctic air gotten cleaner?
Russia.
Well, that's the proposed explanation, that with the demise of the Soviet Union, a lot of dirty factories were shut down in Russia and in Eastern Europe. Also, the Russian Arctic has become depopulated as the subsidies for those inefficient industries have moved. So that means there's less wood burning for home heating, less people there. So anyway, correspondingly, we are finding that the Arctic snow is actually cleaner now than it was. This is Clark and Noon's 60 samples, this is our 1,600 samples. And in the regions where we can compare, we're getting now less black carbon in the snow. And then there's some regions that Clark and Noon did not sample, and so we have them in the more recent. So we don't know what they were previously, but they may also have been different. Summary for the Arctic. Black carbon becomes concentrated at the surface of melting snow. 40% of the absorption of solar energy by impurities is by non-black carbon constituents. And the major source for light absorbing aerosol in Arctic snow is biomass burning, but industrial sources are important in the Arctic Ocean. Arctic atmosphere and snow have become cleaner in the last 25 years. That means black carbon in snow and ice of the Arctic Ocean is probably not contributing to the rapid decline of sea ice in recent decades. You have to look for other causes for that. Arctic snow, as in this picture, is often thin and patchy, so the albedo may often be determined more by snow thickness than by impurities. What's absorbing sunlight there is the surface under the snow. Well, okay, now we go to China, which has the dirtiest snow on Earth. This is a model prediction by Mark Planner, who is a part of his PhD thesis, showing prediction for 1998, black carbon in snow concentration in snow. This is a log scale, so the highest concentrations are in eastern China. Actually, some of these areas don't actually have snow, so what he's calculating is what the concentration would be if there was snow. But northeast China is expected to be very blue. So we did an expedition by car. We drove up through Inner Mongolia and northeast China, and to these locations. Actually got a few on the Tibetan Plateau also. Turns out that there's quite a divide here. this region is desert and it's mostly dust. And this region is black carbon. So, oh, my co-workers from China, it's a different set of names than for the Arctic. Coal is much in evidence in China. Coal, 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 coal. And it's burned in dirty chimneys, seeds everywhere, and of course it gets into the snow. However, we started out in Inner Mongolia, where it's not black carbon, but instead it's soil dust. The snow is thin, and there's lots of grazing animals, and just the sheep kicking through the snow can kick up some soil on the nearby snow. So this, we would call this short-range transport through the atmosphere. It went a few centimeters, and then it fell out. In one day, very unusual day, we actually saw little sand dunes on top of the snow. Okay. Okay, anyway, so these are our comparison filters. The ones on the left are from Inner Mongolia, they're brown. Ones on the right are from Heilongjiang in the northeast, and that's forested area and agriculture and industrial, and they are gray. Now, if we go actually a transect from the Russian border at 51 degrees, going down in toward the industrial areas of China, we see a very strong gradient with latitude as we get to the more polluted snow. So this is a log scale, black carbon parts per billion, as a function of latitude, and the values, oh, and also compared to Flanner's model. And on this log scale, they look pretty good comparing to our measurements. But you can see 1,000 to 2,000 parts per billion in these 42 degrees, but dropping off to about 30 at the north end. And in fact, that's the same value we get 2,000 kilometers farther north at the coast of the Arctic Ocean in Siberia. So it looks like, just from this picture, from the point of view of snow, the pollution that's produced in China stays in China. Now we know that's not true for everything, because this pollution comes across the Pacific Ocean to North America, and gases in particular. But okay, so that's China. This is North America. We did a trip, started in Seattle, and did 67 locations in North America with Sarah Doherty, Chen Dong, and Rudong. Chen Dong was a student at the University of Washington, and Rudong was on the Chinese expedition, and came on this one too. We used a Ford truck, and we drove 10,000 miles. This is in Oregon, and took a picture every time the students from China entered a new state or a new Canadian province. This is our cleanest site, Southeast Oregon, 5 parts per billion. Idaho, a few pictures from our trip. North Dakota, farmland. Oh yeah, sometimes we would go in to ask the farmer for permission to collect snow off their land. On a frozen lake in North Dakota, frozen river, Minnesota, and again, filtering in the hotel room. Manitoba, we went up to the end of the road at Gillen, and then we got on a train to go farther north up to Churchill on the shore of Hudson Bay, walked out on the sea ice, and collected snow at the forest tundra boundary at Churchill. And our coldest site was in northern Saskatchewan. Okay, our North American results from 500 snow samples. yeah, divided into 4 regions. Canada were the cleanest, Pacific Northwest, Rocky Mountains, the dirtiest, were in the northern plains. But these are, oh, I should say, these are not, oh, actually, these are the black carbon mixing ratios. However, the northern plains, the main absorber was soil dust, because there's plowed fields and a lot of soil gets into the snow. The median was 20, so keep that number in mind when we go on to compare with Chile. Oh, but yes, Antarctic. We have made mention, we were in the Antarctic for other reasons. The Antarctic snow is so clean that the black carbon has no effect on the albedo, but it is measurable. If you pour enough water, melt water through the filter, you can get a little signal eventually. You had to put 10 liters of water through to get a signal, whereas in China, sometimes only 10 milliliters was enough to get a signal on the filter. Yeah, so anyway, our Antarctic sea ice, did that with Maria Fatco. And here's our global overview. Also the Antarctic plateau, similar values. 0.2 is our lowest values of nanograms per gram. Our highest value is 2,000 in northeast China, so we go over 4 orders of magnitude. Yeah, so the Antarctic is the cleanest, and the Arctic Greenland is the cleanest part of the Arctic, Arctic Ocean, Arctic Canada, Arctic Russia. Northeast China, I showed you that. I didn't show you northwest China, but the students from China on their own then, after they learned from me, they didn't need me anymore. The next year they went out to northwest China and got these values, 2,600, median of 70, Western North America, median of 20. Chile. So just this last month, yeah, the snow in Chile does not cover much area, so it has little effect on large-scale climate, but it's important for hydrology, for the water flow into the rivers. And this project was funded by grants to Neshida and Raul Cardero. Started out in Arica with Jose, Penny, and Alec. Set up a lab in a hotel room in Putre for our first measurements. Our first measurements were on this mountain Ta'apaca above Putre, and we were able to get to the snow. This is from where we parked the truck, and we got to the snow. It's at 5,300 meters, 5,300 meters on Ta'apaca. This was actually a new snowfall. A little bit of snow had fallen. What was under the snow, we were surprised to find, was really hard. It was almost ice. It was actually snow that had melted and refrozen, so we just could chip away some chunks. So we got the thin new snow over the ice. And the next site farther south we went was above San Pedro de Atacama, where there's a couple of astronomical observatories, and there were roads going up to them. And the road actually goes up to 5,300 meters here, and then we went up into this area to sample the snow. And this astronomy observatory also has its own source of black carbon. So we tried to get away from it and went up there. You can see the observatory down there in the background. We climbed up onto this Cerro Toco and dug a snow pit. And then the third place, coming farther south, east of Chañaral, we were able to get up the road as far as 3,500 meters at a road patrol station at La Ola, July 14th. So this was new snow. This was the storm of July 13th that produced rain in Santiago and caused snowfall all the way up from here on up, at least this far. So this was a very important storm for us because it provided us some snow to analyze at moderate elevation that we could get to in all these locations south of this location. We were in the snowstorm here. In fact, we couldn't see anymore there was a blizzard. What's the word for blizzard? Ventisca, yeah. So this was as far as we could get, but fortunately, this place was occupied, and they welcomed us to come in and stay overnight and cook lunch for us at La Jolla. And then we went out in the morning. The weather had calmed down. We could then see. And this place had so the snow fell during an intense windstorm, probably mixed with dust. But then some snow fell in calm after. So we got an interesting vertical profile here. And then we drove out back to Salvador, and then south to La Serena. So that was our next location, up the Elqui Valley, east of La Serena. And that's where Mikhail joined us. Shelley McDonald was our guide here. She works at the SEASA laboratory there. And then Raul also came up for a day of snow sampling. And there he is, like in our right here. So above the Elqui Valley, the road is down there, and we just want to get up above the road. Next, Stephen and Mikhail and I continued south. We went up to the Maru Valley, and then the Chilapa Valley. We got fairly thin snow, but we were able to sample it. And then went to Portillo ski resort, and up behind the hotel, behind the ski lift, there's a lake, and we went out onto that peninsula in the lake, and that's where we did our snow sampling at Portillo. Yeah. Oh, and we like to keep our snow frozen until we're ready to analyze it, and then melt it quickly. The reason for that is that if you have meltwater for a long time in contact with surfaces, the soot, because it is hydrophobic, will go and stick to the glass or to the plastic. So we keep it frozen until we're ready to melt it quickly in a microwave oven. So we had to store we had to find freezers to store our snow. And this was we're at our hotel below Portillo. They had sold most of their ice cream, so they had plenty of room for our snow, along with the remaining ice cream in this. The highway there, there's a Trans-Andean highway going across over to Argentina, and maybe 1,000 trucks per day. So we were interested in the pollution by those trucks. And so we went out the side valley, a road going the Puncal Valley, going southeast from the Trans-Andean highway. We sampled snow at different distances from the highway to see if we could see a drop-off in the pollution from half a kilometer, 1 kilometer, 2 kilometers, and then almost 4 kilometers. And then we came down to Santiago. We went out into, actually Gino Casasa got us up into our sampling location in Maipo. Okay, now here's some results. Well, these are visual estimates, of course, because we haven't yet gone to the spectrophotometer, but last night, this morning, we have visual estimates. We've got about 180 filter samples, and these are what I call black carbon equivalent. So if the dust is doing the absorbing, we ask the question, well, it's actually dust, but how much black carbon would you need to have the same absorption? So this, in the North Atacama region, it's actually dust, but it's equivalent to 30 nanograms per gram of black carbon. So that latitude's 1823. And the rest are all from this one snowfall event that happened on 13th, 14th of July. So here we are, sites, this is latitude, and then as we moved south, the snow was aging. So we were anywhere from 0 days up to 12 or 13 days after the snowfall that we collected the snow. And then here are the values of black carbon equivalent in the surface value, the top 5 centimeters, and then the subsurface. So for this first one, as I said before, there was a blizzard, Dentista, that I suspect is responsible for these high values in the deeper snow. It's mixing dust in. And then the surface snow was actually cleaner. But as we go farther south, maybe the winds weren't so strong. But anyway, the deeper snow is very clean. 2 to 4 to 5, I mean, it's really very clean. You don't find snow that clean in North America. Antarctica's cleaner, but this is, I suppose it's just because we've got clean air coming off the Pacific Ocean, and that's where the snow's coming from. Now, after the snow fell, though, there is dry deposition of aerosols that is polluting the surface layer. So the surface values are higher than the subsurface values and actually increasing with time as we move farther south. The highest values were at the ski resorts east of here, Valle Nevado and Farallones. But also the microvalley. So we're seeing pretty consistent pattern where the subsurface snow is clean and the surface snow is dirty. So we interpret that to be due to dry deposition after the snow fell. There's been no snow falling since then in the last 2 weeks. So here, for example, are filters that Penny arranged in vertical order from Valle Nevado. These are the top 5 centimeters, 5 to 10, and 15 centimeters. Now, why don't these all look the same? It's because, let's see, I guess she did this one, and then she said, oh, that's too dark. I'm going to put less water through the next one. And then, oh, it's still dark, so I put less water through. So they're actually the same concentration, but there's less water went through the filter for this one. So, our preliminary conclusions for Chile. Dust dominates the absorption in the Atacama. We get brown filters. Black carbon dominates the absorption near Santiago. We get gray filters. The snowfall of 13th, 14th of July was clean, except where mixed with dust in the strong wind during the snowfall event. The surface layer became polluted over time by dry deposition. Also, I didn't show you this result, but when we went transect away from the Trans-Andean Highway, those 4 locations, the surface values were all the same within their uncertainty. So the black carbon from the diesel trucks is not being deposited quickly near the highway. The black carbon mixing ratio did not decline from half a kilometer to 3.6 kilometers. So it may be entering long-range transport. That's all. Thank you.